The final thing we need to talk about with respect to chemical reactions before we move on to actual stoichiometry is the difference between endothermic and exothermic reactions. And really what that's meaning is that we need to look at how energy transformations are made during chemical reactions. So when chemical reactions occur, bonds between the atoms that already exist are broken and new different bonds are formed. So looking at this animation, we can see that there are bonds here that exist between atoms in molecules before. The old bonds of the reactant must first be broken. Then the atoms are able to rearrange themselves and form new products when new bonds are formed in the products. Now, energy is required to break any existing bond. There's this idea that some bonds can be broken and some bonds can be formed without actually requiring energy. But no, all bonds require energy to break. The reaction will continue until the reactants, either one or both, are used up. Now, we can start that reaction by giving some form of energy, usually heat or light, electricity. Sometimes we can use kinetic energy in the form of agitation or mixing, etc., etc. Now, enthalpy is a measure of the heat content within a system. When I say a system, what I mean is that it's the container or the vessel in which a reaction is occurring. And generally, we measure that in units of kilojoules per mole. So looking at exothermic reactions have heat given off during the reaction. Because the heat energy is left less after the reaction, that means then the change in heat content, the change in the stored heat energy of the reaction is less after the reaction before. Now, keep in mind that energy is not created or destroyed here because of the law of conservation of energy. It's just changing form from one kind to another. So if energy is being released, then it must have been stored energy before. By the same token, if energy is being absorbed later on, then that means that the energy must be coming from some other kind of form. Now the reactants then contain more heat energy, more stored heat energy than the products do. And as a result, we say that the delta H is negative. Anytime you do a calculation and you see that triangle or delta symbol, delta represents a final condition minus an initial condition. And because when I say the H value represents the stored energy, if there's less stored in the products than there was stored in the initial reactants, then that delta H has to be negative. Because of that, the products happen to be more stable than the reactants because the products have less energy. And when the bonds were broken, in any case, when bonds are broken, we have to remember that energy is needed or absorbed. And when those bonds are formed, then energy is released. So how does this get drawn out on an energy transformation diagram? For those of you that take Chemistry 12, you'll look at this diagram over and over again, and having some basic familiarity with it before going into Chemistry 12 will put you at a huge advantage. So what I'm saying is that the reactants have some amount of energy. Unless you're given a specific amount, you won't know how much. But they do have stored energy in the form of bonds. Now, in order to break those bonds, we must put in energy. So the energy goes up to some maximum. In grade 12, you'll call that an activation energy. But for now, you just need to know that there's some maximum value. Now, as bonds are being reformed, energy is given off. And what we see with an exothermic reaction is that the energy stored in the products, down here, is less than the energy of the reactants, and as a result, we have a negative delta H. So on this diagram, we would show that the products are lower than the reactants were in energy, meaning that our delta H value here is negative. And keep in mind, regardless of the reaction, energy is needed or absorbed in order to break the initial bonds. All reactions require that first input of energy, and energy is released by the bond formation as we get products being made in the end. Now, because with exothermic reactions, we have this extra energy being released, we have enough energy to break more bonds. This means that the reaction will continue on its own without any additional energy input until one or both of the reactants is used up. The additional energy that isn't being used to break more bonds is then seen in the form of heat or light. When we write an exothermic reaction, the energy is going to be written as a part of the products. So for example, we might see that sodium reacting with water to produce hydrogen gas and sodium hydroxide is exothermic because it has heat or energy or some specific number of kilojoules, which just means an amount of energy. All of those terms are synonymous and could be used interchangeably. Now, endothermic reactions are a whole different story. What we see with an endothermic reaction is that heat is absorbed during the reaction. Because the heat energy is absorbed, that means that the heat content of the products is greater after the reaction than it was before. Again, remember, energy is neither created nor destroyed, so if the heat's being absorbed, they must have had it come from somewhere. The reactants then contain less heat energy than the products do. And as a result, the delta H is positive. So we know that our delta H is our final minus an initial. We have more stored in our final. The final is greater than the initial, so your delta H value will be positive. But that does mean now that the products are less stable than the reactants were because the products have more energy, making them more likely to be broken or have those bonds be broken in the future. Just like before, I've already said, any chemical reaction requires energy to break the existing bonds. Energy is then released when bonds are being reformed. The trick here is that the energy that's released by the bond formation is less than what we would need to break more bonds. So looking at a diagram here, we have reactants that have some amount of energy. I'm not quite sure how much. You would have to be given that in a question. We do know that it's again going to require energy to break the bonds to some maximum, and energy is again given off when bonds form. But this time, the energy stored in the products is greater than the energy of the reactants. So on our diagram, we would see that our delta H value here is positive. Now, because the energy that is released is less than the energy that it would take to break more bonds, a constant source of energy needs to be supplied in order for these reactions to continue. If you don't continue to supply the reaction with energy, then the reaction will stop. So a common and easy reaction for people to think about in this particular case is the reaction changing water from its liquid form into water in its gaseous form. That reaction requires heat, because it's a requirement is written on the reactant side, or energy or you could be given some specific number of kilojoules. Again, these are all used interchangeably. What I've said to you now is that if you do not supply the heat, then that reaction is going to stop. And that's what you would observe. You put a pot on a stove, and once it hits that temperature, if you continue to supply it with energy, the water will continue to boil, turning it into a gaseous form. As soon as you remove that source of heat, that reaction is not going to continue anymore. So once we get to class next day, you're going to be asked to do some practice regarding energy transformations and transfers in a chemical reaction. Also next day, you're going to be doing a lab that will let you see and observe how these reactions actually look.